Yes, class. Good evening.
Good evening, ma'am.
Fatima, Hamza, Hiba, Huzefa, Krishna, Sarah. Okay, 6 students have joined till now. So refraction we had started. The refractive index was earlier done. Reflection we have completed. And we had completed with the lateral shift, lateral displacement and refraction through compound plate, and the basic definitions and the laws of refraction. All these topics we had completed. Now one topic is apparent depth and another topic is total internal reflection. These are very important topics before we begin with the spherical lens. Mirrors we have done in reflection. Similarly, we have the same things in case of refraction with regarding to the lens. Lens formula will also come the way we had mirror formula. But before we begin with all those things, we'll start those things in the next class. We have apparent depth and total internal reflection. These two are very important topics for all the theoretical part as well as for your numericals part as well. Numericals also come and theory part also come. See, apparent depth is very easy to understand. Apparent depth means, for example, if I take a glass of water, fine, and I put a coin inside it. Now, if I put a coin inside it, if this is the actual depth of the glass, coin is over here. But when I look it from here at the surface, if I am viewing, I'll be able to notice that the coin is visible over here. So has the coin raised inside the water? Definitely not. Density of coin is more than the density of water. So coin cannot float on water. If coin is sinking inside the water, then how is the height changing? So it's actually not the height that is changing. It's because of the refraction that is occurring at the surface. So the depth that is not actually present, which we are able to see because of the straight lines or that straight rays that pass into our eyes. For example, C class. If I take a beaker, see, I have, for example, I have taken a glass filled with water. Now at this end, I have kept a coin. Fine. This is a coin that I've kept. So all of you can notice from the surface of the water till this coin, this is the actual depth of the coin. If I ask you to measure the length, this will become D1. This is the actual length of the coin. Now what will happen? See, now our object is kept in the inside the water. This is air. Air is your rarer surface, and this is water. Water is your denser surface. Water is denser. Now, see class, wherever you have objects, rays pass from that. Wherever the object is kept, from there only you have the rays passing. So coin is kept at the bottom. So it means now light rays will come from here. Had the object been kept over here, then we would have sent our rays through it. Now the coin will be sending its rays. So rays will come. Now this will be the normal, this will be angle of incidence. All right. Now since it's an interface between water and air, two media are involved, so definitely refraction will occur. We have studied refraction, laws of refraction and all these. So we know at this point refraction has to occur. Now refraction will occur. Ray of light will get reflected. This is angle of refraction. Fine. Now see, if I produce this line, see, I am able to see this. So if human eye is kept if a human eye is over here, if you are viewing this, so will you be able to see this bending? Will your eyes be able to see this obliquity that has arisen, or the shift in the angle that has arisen, or your eyes will see a straight line? Light travels in a straight line. This is a property that we all are aware of. So if we see, we will be able to see just this line. We won't be able to see this deviated path, right? So that's why the coin appears to be at a greater depth than it is actually present. It appears to be shallower. You see the coin at a very different depth. Now, this depth that I'm able to observe, this is known as the apparent depth. Some more rays I'm drawing just for the calculation part, because we have to do the derivation. So for that, so this is D2, fine. Now, this gap that you're able to see, actual depth and this real depth and the apparent depth, there's a shift in the image of the coin. You were able to see the coin here, now you're able to see the coin above. So there's this shift. This part is known as shift. Shift is simply the apparent displacement that has occurred of the coin. This is not an actual displacement. We all know the coin is kept at the bottom only. But since these rays of light are straight away passing, we cannot see it bending. Because otherwise then the phenomena of refraction was of no use if the light didn't travel in a straight line. Fine. So here what happened? We are able to observe this image. Let's say this is O1, this is O2. Let's name this interface as well, because we'll be needing this A point. This point I am naming it as B. Now, one more thing before we start. C class, if you look carefully, notice here. See this ray AO1 and this ray, this B, where refraction has occurred, this normal, both are parallel to each other. If this O1B acts as a transverse, then angle of incidence over here, this will be equal to angle of incidence I, because of alternate angles, right? These are parallel lines and this is acting as a transverse. Also, if these are parallel lines, then O2B is also acting as a transverse. See, O1B was acting as a transverse. So these were equal because of alternate angles. These two are parallel. O2B is also acting as a transverse. So this angle is angle of refraction. This will be angle of refraction by corresponding angles. Understood? Right, so this is angle of refraction, this is angle of incidence. All right, wherever you're not able to understand, stop me, I'll repeat it. Fine. So D1 is what? D1 is actual depth. This is the real depth. Real depth of the coin. And D2 is what? D2 is the apparent depth. D2 is the apparent depth of the coin. Now a very small derivation. We have it to prove or to get the relation between the refractive index, the apparent depth and the real depth. Formula is very easy to remember. Derivation you have to see. Derivations are there for 4 to 5 lines, but the formula is very small, so you'll be able to remember the formula. See, if you notice this triangle, O1, AB, this very big triangle from the coin till the surface, O1, AB. In triangle O1, AB. If I try to write down value of sine I from here, see this will be what? Perpendicular upon hypotenuse. So perpendicular is AB, hypotenuse is O1D. So this becomes AB divided by O1D. Fine. Now if you see the smaller triangle, O2AB, this smaller triangle, what will be the value of sine R now? Yes, class. O2AB, value of sine R. Simply see this triangle. Should I call out names? Simple trigonometric.
AB by O2B.
AB divided by O2B. Yes, Fatima. So only Fatima remembers the trigonometry. This is AB divided by O2B. All right. Now we have these two equations. Now let's just divide these two equations. This equation that we have and this equation that we have. Fine. Sin I and sin R. So if you divide, you have sin I by sin R. Sin I will be AB by O1B. This will become O2B by AB. AB gets cancelled. We are left with O2B by O1B. A very small approximation you have to use over here. See, this point A and this point B, this I have drawn it very broadly, no, but in reality, these two rays are not very far apart. Point A and point B are very close to each other. If point A and point B are very close to each other, so it means the length or the distance will also be same. If A is at a separation of, let's say, 5 centimeter from the coin, and B is just close to A, B will also be at a separation of 5 centimeters. What I'm trying to say is, if A and B are very close, if point A and point B both are located very close to each other, then according to an approximation, we can say that O1B can be written as O1A and O2B can be written as O2A because these points are very close to each other.
Teacher, I did not understand this.
See, this part now from here. See, A point and B point are very close to each other. Whenever a coin is placed, this line is not an actual line. Actually, this angle of incidence is very small. This is very small angle. So these are looking like this, but these rays are like this. Fine. So if when we see this, if these two rays are approximately equal to each other, so if I write O1B or if I write O1A, will there be any difference? No, approximately they'll be same. That's what we are going to use because O1B, O2B, why are we implying this? Because there was no need, we could have solved it. The reason is that because we do not require O1B and O2B, they are of no use to us. We require in terms of apparent depth and real depth. So if we use the only way to substitute O1B and O2B in terms of O1A and O2A is by using the approximation, and this is true that these rays of line from a single coin cannot go into such diversions. If it is generated from a small coin or any object as well, then the rays of light will be very close to each other. So both of them approximately will have the same height. Fine? This is clear, Fatima? Okay. So now I'm replacing O2B and O1B. So if we use approximation, points A and B are close to each other. So we can simply say O2B is approximately equal to O2A and O1B is approximately equal to O1A. Now we have our terms and the formulas in terms of real and apparent depth, because we all know what is O1A. This is the real depth D1, and what is O2A? This is the apparent depth that has shifted, apparent depth D2. Now we can get our answers. So see, sin I by sin R, this is equal to O2A by O1A. O2A was the smaller one, that was the apparent depth. O1A, this was the greater one, that was your real depth. Fine. So D apparent by D real is sin I by sin R. Now, what was Snell's law? What was Snell's law? Akifa, can you answer? Akifa Abdul Basir, what was Snell's law? Snell's law we had done in the last class, in the second law of refraction. Akifa. Akifa, you present in the class? Yes or no? In the last class also there wasn't any response. Okay, she's there. Ratio of the sine of the angle of incidence to the sine of the angle of refraction is constant. Very nice. This was Snell's law. Sine I by sine R. This is what? This is a constant that we know, which is refractive index. So if we apply Snell's law, see, if you apply Snell's law at this point, no. This is air whose refractive index is 1. And let's say the refractive index of water or this medium or this liquid. I'm not referring specifically to water because then it will not become generalized formula. Then you'll be able to only use it for water. So let's say N, some liquid is there. Apparent depth can be visible in any liquid. So this will be 1. Understood? This is 1. Now multiplied by sine I. Or simply you can use, see here you have angle of refraction. So you can say 1 into sine R is equal to N into sine I. This is also one method that we have seen. Why? You can apply Snell's law at this point. This will become easier. Then you can substitute it for here. Because this is a little difficult. You have the labelings and the shift also. If you just see this point, the refractive index of this area multiplied by sine of this angle is equal to refractive index of this area multiplied by the sine of angle. So 1 into sine R is equal to N into sine I. Also we can say 1 into sine R is equal to N into sine I, or you can simply say the law that Akifa has stated very well, sine I by sine R will be 1 by N. Now, if we put it sine I by sine R, this was d apparent by d real. D apparent by d real. This will be equal to 1 by N. So formula of apparent depth becomes whatever is the real depth divided by the refractive index. So this was a little lengthy derivation, but the formula that we obtain is very small. D apparent is D real divided by the refractive index. One more thing. Can any one of you tell me how can we calculate the shift? This whole was the depth. Then the shift in the coin was the apparent depth that we were able to observe, that gap that we are getting. So how can we calculate the shift? Sarah, can you try? How can we calculate this shift? By looking at the diagram, then I'll tell you. If you just let me know the first step. Sarah, just try Sarah once. Krishna?
Ma'am, D1 minus D2?
D1 minus D2. Exactly. This will be D1 is, see, this complete is D1. And the apparent depth was D2. So this gap, this is obtained. This is known as shift. Fine. The shift that we are able to observe in the image. So it will be simply D1 minus D2. Understood? Sarah and the rest of the students. So shift will be simply D1 minus D2. Or we can even write it in terms of D real minus D apparent. And we have the formula of D apparent now. D apparent is D real divided by refractive index. So from here you get the formula of shift as D real depth multiplied by 1 by one minus 1 by N. This is the formula of shift. Fine, this is the formula of shift. Now, one more thing. See, it's not necessary that, see, if when we take this example that I've started with, when you observe this example, what are we able to observe? That apparent depth is greater or the real depth is greater? What do you think by looking at this?
Real depth is greater.
Real depth is greater because apparent depth, the object is appearing closer to ourselves, to our eyes. So apparent depth is less, but this is not always possible. Why was this possible? Because our object was inside the denser surface. So if your rays of light travel from denser to rarer, that time your real depth becomes greater than apparent depth. I'll write down this because this is important for your theory part. See, if light rays travel from denser to rarer, the way it was traveling right now, that time your real depth, as you can notice in this example only, becomes greater than apparent depth. But if you have an object that is kept in air and you are able, or not even in air, in any medium which is rarer, so if the light rays travel from rarer to denser, if your object is kept inside the rarer medium and you are observing from the denser medium, in that case you will see object is not shallower now. Object is now at a depth. Object was there at a certain distance from the surface, but you will be able to see it as at a greater depth. So that case your apparent depth becomes greater than real depth. All right. So numericals, let's do it after you write this down so that any queries and doubts you have, you can get it clarified. So this was all about your apparent depth. This is just the formula. Derivation can be asked, theoretical questions can be asked, and numericals also can be asked from this. See, this question says apparent depth of an object at the bottom of the tank filled with refractive index 1.3. So refractive index is 1.3 and the apparent depth is 7.7 centimeters. And what is the real depth? So very direct question. Apparent depth is equal to real depth divided by refractive index. So real depth will be equal to refractive index multiplied by apparent depth. So D real will be 1.3 into 7.7, this much. So I think this will be 10.01 centimeters. Just cross check one, is this the answer? Fine, easy. One more question we'll do based on shift. 10.01 Sara, no? Okay, then this will be the answer. Note this down. Then we'll do one more question based on shift, then we'll move on to total internal reflection. Question 2 says a mark is made at the bottom of a beaker and a microscope is focused on it. So a mark is made at the bottom of a beaker and microscope is raised through it. If you have a beaker over here, this is filled with water and a mark is made. Mark is made. Okay, and microscope is raised through 1.5 centimeters. It means now the mark will appear here. This is 1.5 centimeters. Fine, now we are able to see the mark over here because it has been raised. Then it says to what height must water be poured into the beaker to bring the mark into focus. It means what is the actual depth of this water? How much is the water present in this? What is the real depth that is present inside this water? And refractive index of water is given to us as 4/3. Can anybody tell me what is this 1.5 centimeters given?
The shift.
Yes, good. It's the shift. See, this is the original depth. This is the apparent depth. So there's this gap between, or the difference between the apparent depth and the real depth is the shift. So see, you have the shift as 1.5 centimeters. Refractive index is 4/3. And the real depth is asked. So one formula we have seen on this. We can implement it directly here. Shift is equal to what? Shift is equal to real depth 1 minus 1 by n. So this is 1.5 is equal to d real is unknown. 1 minus, okay, 1 by n. So that becomes 3/4. 1.5 is equal to d real 4 minus 3/4, that is 1. So d real will be 4 into 1.5. So d real will be 6 centimeters. All right. Note this question down, note the solution down, and from this topic, apparent depth, whatever queries you have, you can ask me because this was about this topic. Now we'll start with total internal reflection. So if you have any queries, if you have any doubts, let me know. Note this down. You can turn the pages and see from the starting of this topic if you have any queries. All right. Note this down. Now see total internal reflection. All the phenomena for refraction that we have studied will go as well. See, rarer medium is there, denser medium is there. This is the rarer medium, denser medium. Whenever you're drawing this, try to draw it with the help of scale. Here the ruler is not working on the screen. Anyways, now see, if a light ray travels from the denser medium, the light ray is incident from the denser medium. Fine. This is denser medium, right? So this is angle of incidence. And so there will be angle of refraction. Fine. Angle of incidence and angle of refraction. All right. Now what will happen? No, I shift this. I increase the angle of incidence. I shift this a little bit. If I shift this a bit, what will happen? Angle of refraction will also shift a bit. So angle of refraction increases. This also increases. Fine. Now what will I do? I'll shift it a little more. Now when this refracted ray will be shifted, this will graze over it. Ray grazes over surface. Ray grazes over surface. So this angle is what? Angle of refraction is 90 degree. This was what? See, this was the refracted ray. This was the incident ray. Ray was incident from where? It was incident from the denser to the rarer surface. And this angle, when the ray grazes over the surface, or you can say at this angle, when the angle of refraction becomes 90 degree, so that angle of incidence is known as the critical angle. Critical angle is what? This is the angle for which the refracted ray grazes over the surface, or you can say this is that angle for which the angle of refraction is 90 degrees. This is critical angle. Now, if I exceed my incident angle more than this critical angle, this three cases I have obtained, these three cases. Now, if I extend this incident angle more than the critical angle, this time the incident angle, I have exceeded it from the critical angle's value. Now the ray will go where? The ray will come down, because now 90 degree was the maximum value that was possible for a refracted ray. Now if I increase the angle of incidence much greater than critical angle, it will suffer from reflection. This refracted ray has now become what? This has become a reflected ray. This is now a reflected ray, and this is now angle of reflection. This is angle of reflection, and this phenomena where your incident ray is moving from the denser to rarer medium, your angle of incidence is greater than critical angle, and the refracted ray becomes reflected. This phenomena is known as total internal reflection. This is what is meant by total internal reflection. Total internal reflection. For total internal reflection, two conditions have to be there. For without these conditions, you will not have total internal reflection occurring. First condition, ray should travel from denser to rarer. Here you will not have another case where your ray of light will travel from rarer to denser. Denser to rarer is fixed. And second thing, angle of incidence should exceed critical angle. If it exceeds, then only though this ray of light will get reflected. Otherwise, if this is still the value of critical angle, you will have angle of refraction as 90 degrees. Understood?
Yes, ma'am.
Huzaifa, what was the first rule? Huzaifa Ahmed, what was the first rule for total internal reflection to occur? First condition that I have told you all, or any one of the conditions, specify one of the conditions and write it in short if you're writing. That's why I ask you all to unmute yourselves. That's better. Only few students are always unmuting themselves. Fatima is there, Krishna. These are always unmuting themselves. Yes, Josefa, do you remember or not? At least answer yes or no. Because without any response from here, it becomes difficult. Okay, light travels from denser to rarer medium. Angle of incidence is higher or greater than the critical angle. Perfect, Josefa. Very good. Hiba, what is critical angle? Hiba, what was critical angle? Hamza, what is critical angle? See, everything is written on the screen right now only. Critical angle. Fatima, yes, Fatima.
Teacher, when the angle of reflection
Refraction,
is,
refraction.
refraction, sorry, grazes over the surface, then the angle between the normal and the angle of refraction is 90 degree, and the angle of incidence is critical angle.
Yes, perfect. 2 points you have to remember in critical angle. Ray grazes over the surface and angle of refraction is 90 degrees. Now tell me all of you, is this clear? I'll repeat the definitions. If anybody has doubt, please let me know. Definitions I've already written. The phenomena in which a ray of light traveling at an angle of incidence greater than the critical angle from denser to rarer medium is totally reflected back into the denser medium. This is known as total internal reflection. And what is critical angle? The angle of incidence in the denser medium for which the angle of refraction in the rarer medium. This is 90 degrees. This is called the critical angle of the denser medium and is denoted by I with a subscript C, or this is also written as sometimes capital C as well. Fine. This is what is meant by total internal reflection. Ray of light which was supposed to get refracted is now getting reflected, where reflection and refraction are two separate phenomena, but we are able to see that this ray of light is getting reflected. See, from total internal reflection, specifically this phenomena, you have questions, you have applications of total internal reflection. Some of the phenomena you must have heard of. Optical fiber, have you ever heard of optical fibers that are used in these computers and laptops? Or have you heard of that phenomena that occurs on a sunny day, mirage? So all these phenomena, these are applications of TI that we'll do in the next class. We'll see this part. So from TIR, theoretical questions and explanation with this diagram that I have shown is asked with the two definitions. Numericals come from your critical angle. See, critical angle is very important. This is, let's say, refractive index of rarer medium, refractive index of denser medium. Light is traveling from the denser medium to the rarer medium. So angle of incidence is critical angle. This is angle of refraction, which is 90 degrees. See, NR into sine 90 will be equal to ND into sine IC. I hope now the application of Snell's law is clear to all of you. Application of Snell's law, how to apply the law, how to write down the statement. You can directly write sine IC by sine R is ND by NR. But it can be confusing whether it is NR in the denominator, ND in the denominator, that can be confusing. So wherever you have the refractive index, let's say this NR. So write the angle, sine of angle of the sine of angle that is present in this. That is your sine R. This is equal to ND into sine IC. So NR into sine 90 degrees is equal to ND into sine IC. Fine. Sine 90 is 1. So NR will be equal to ND into sine IC. So sine IC can be written as 1 by NR by ND. And NR by ND can be written as 1 by ND. This can be written as 1 by NDR. So this is the value of critical angle whenever I'm writing NDR. See, NDR is what? This is refractive index of denser medium with respect to rarer. So NDR is what? This NDR is NR by ND. So that's why I've written it as ND 1 by NDR. Fine. And this is refractive index of denser medium with respect to rarer. See, questions can be asked. Simple questions can also be asked to you. For example, let me give you one question. One very easy question. Then tougher questions you have. From critical angles, you get good numericals. So do practice critical angle. See, whenever we discuss any topic, we have any topic, I keep on telling you about all the importance of that topic, whether it's difficult, whether it's easy, you need to emphasize on it, or it can be done easily whenever. So this I'm telling you, critical angles questions are tough. Some of the questions that have come in your exams are tough. So practice critical angle well. Though this is a very small topic and the formula is also nothing. Sin IC is 1 by NDR. But questions from here you have it. We'll do certain questions in the class, but you need to practice by yourself as well. Calculate critical angle for glass air interface for example, this is a question. Now, for glass and air, it's not given. 3 things I'll suggest you to learn in this lesson. Refractive index of glass as 1.5, refractive index of air as 1, and refractive index of water as 1.3. It can be used. Sometimes it cannot be given in the question. So by mistake, if you're stuck in the question in your board exams, you should remember these 3 things. All right. So see, NDR will be what? This will be denser is glass, rarer is air. So that becomes N glass divided by N air. So 1.5 by 1. Or for sin IC, you can simply reciprocate it 1 by 1.5. So critical angle will be simply your inverse trigonometry, sine inverse 1 by 1.5. This will become the angle. This was a very easy question. Certain questions, certain good questions are there in NCERT. That also we'll cover. In NCERT also you'll find questions. As I see, this is your answer. Do one thing, note this down. That's why I was asking all of you. If you have any doubts in TIR, let me know. See, this concept of TIR is easy and concept of critical angle is also easy. But numericals are there, which have come in your previous years, which are good numericals. So do practice this. You have this weekend. One more thing. Next Thursday, see, now we are left with lens part, where you have the same things for lens, optical instruments, and prism. I think till the time we'll be completing it, you will forget reflection, what we have done. So reflection, laws of reflection, mirror formula, that part that we have completed, not the refractive index. I'll take a very small test on next Thursday. Fine, a very small test I'll take. Questions will not be difficult. Mirror formula, you have question based on mirror formula for all concave, convex mirrors, the images formation that we have done. That reflection part that we have completed, I think in 1.5 classes we had completed it. That will come. So start revising for reflection also. Why did we write IC/C in the critical angle definition and not only IC? See, both are represented. And I have written because if by chance in any of the books, reference books, if you are referring to or somewhere in the notes or somewhere, you find and critical angle written simply as C. So do not get confused. Both are same. Critical angle is sometimes denoted by just capital C also. That's why.
Thank you, teacher.
NR by NG become 1 by NDR. See, you can write it as 1 by NRD as well. See, the second ray, no, the second ray. Second ray means the medium in which the ray is entering. That is written first. So this you can modify by yourself also. Like in this, you write N2 by N1. Remember whenever we used to write Snell's law, Sine I by sine R. We used to write it N2 by R, N1. So N2 by N1 can be written as N21 as well. Refractive index of second medium with respect to first one. So you can shift this according to your need. For example, in this question, it was glass with respect to air. So glass will come first and then air, because we know from air the light is entering into the glass. So glass refractive index will be written first, then airs. And this is 1 by NGA, which is written as 1 by 1.5, like this. So this writing partner of the variables, this is up to you. You can write it by yourself as well. It's just that it becomes reciprocally, you can write it, or you can leave it in terms of this only. It's just a way to concise it, because if just one angle is given, so you can use sine IC is equal to 1 by n. वो तुम्हारे ऊपर है, ठीक है? However you feel it, you can use it and modify it. Okay, Sarah? See class, the complete question I'm not writing. From here only we'll start with this question. This question says a glass slab is there. This medium above is air. This is air whose refractive index is given as 1. This is what? This is glass. And incident ray is incident with the angle of incidence as 70 degrees. Let's name these points. M, let's say this point is N, this point is P. And when this ray gets refracted, here it gets total. Here the angle of refraction becomes 90 degree. This grazes over the surface. So it means which angle is this if it grazes over the surface? What is this angle?
90 degree.
Critical angle.
Critical angle. See, 90 degrees refraction, the inner incident angle. This is 90 degrees, Krishna. And yes, this is critical angle. So this will be critical angle. Fine. All right. So A, B, C, D. Now let's see, the question is actually asking you to calculate the value of critical angle, and you do not know the refractive index of this glass. Though I have told you certain refractive indices you have to remember, but you cannot apply it in all the questions until and unless you are sure that you require it. So that you have to analyze by your own. Now see, if we choose this side, vertical plane, BC, this plane. Let's say refractive index is for the time being N. We'll calculate the value of N, but let's say for the time being it's N. So for this face BC, if you look at this face, here critical angle will be what? Sine IC will be equal to 1 by N because no other medium is there. The second medium is air with whose refractive index is 1. So you can easily write sine IC is equal to 1 by N. Now if you look at this face, AB face, here if you apply Snell's law, 1 is the refractive index multiplied by sine 70. This is equal to what? Refractive index is N, and here the angle of refraction is sine R. First tell me, are you all people able to understand when I write this sentence, or there are difficulties whenever I'm asking this? Understood? All of you?
Yes, ma'am.
Okay, if by chance you're not able to understand, then stop me. One more thing, in this question class, sine 70's value was given, 0.9397. Yes, 0.9397. So 0.9397 is equal to N into sine R. From here, you have value of sine R as 0.9397 divided by N. Now, if you look at this triangle, this is 90 degree, this is R, this is IC. Can you tell me what is the sum of all these three angles? These three.
180 degree.
Good, Fatima. So it is 180 degree. Fatima is totally active in today's class. Yes, angle of refraction plus 90 degree plus IC, this is 180 degree. So this becomes, see, if you use this triangle, in this triangle, this becomes, what was the triangle that we chose? MNP, I think, yes. So refractions angle, critical angle plus 90 degree is equal to 180 degree. So angle of refraction plus critical angle is 180 degree. From here, you can say angle of refraction is equal to 180 degree. Here, this will be 90 degrees. So this becomes 90 minus IC, right? So we can put the value of sine here. Sine R is equal to 0.9397 by N. So R's value can be written as 90 minus IC. So I can write it as sine instead of this R. Now I can substitute 90 minus IC. 90 minus IC, this is equal to 0.9397 divided by N. Can anyone tell me which identity is formed over here? Sine 90 minus theta. is
Cos theta.
good, Sarah. It is cos theta. Yes, Josefa, right. So sine 90 minus IC will be cos IC. This will be equal to 0.9397 divided by n. Now C class, if I write sine square IC plus cos square IC, this is equal to 1. So from here, if I write down the value of sine square IC, I get 1 minus cos square IC, right? And what is the value of cos square IC? 0.9397 by n, or let me write it as 0.94. In the exam, if you have time, you can write it precisely, but writing it every time, I'm writing it as 0.94 only. So 0.94 whole square by n square. This was the value of cos square IC. Cos IC we had, so cos square IC will definitely be this, sine square IC. And one more thing, C class. Sine IC we had already got. Yes, here. Sine IC is 1 by n. So sine square IC will be what? 1 by n square. So from here you can substitute this as well. So if you substitute, you get 1 by n square is equal to sine square IC will be 1 by n square because sine IC was 1 by n. So sine square IC is 1 by n square. This becomes 1 minus 0.94 whole square by n square. Bring this on the other side, that becomes 0.94 square plus this will become this 1 will be equal to n square, right? N square will be the same in the denominator, get multiplied by 1 and n square you will have. So n square will be this, so n square will be 1.88 approximately. So refractive index will be under root 1.88. Approximately you will get this. I have taken this approximation class. It cannot be an exact answer because I'm doing it orally. My purpose is just to make you understand the method of this. If there is any error in the calculation, please correct me in between. So this is refractive index. See, now we have the value of refractive index. Calculation of sine IC is not difficult now. This will be 1 by n. N is 1 by 1 point under root 88. IC will be sine inverse 1 by under root 1.88. This was difficult for us to calculate. Reason was this was difficult for us to calculate. We were not able to get this because we didn't have the value of refractive index. Now we have the value of refractive index, so we can put it in the main formula and get the value for it. Fine. Otherwise, had we known the value of refractive index, we would have calculated it. So we had this equation, n was unknown. So using the other equation, we have calculated the value of n. Now, once we've got the value of n, we have kept it in the main formula. So note down this question. This is from your NCRT only. I don't remember from where, but this is a very important question. And these types of questions not only appear for your board exams, especially for students who are going to appear for their entrances after class 12 board exam. These kinds of questions are very important. And see, such kinds of questions are available for a critical angle. It's such lengthy questions. So that's why I'm emphasizing. Please practice critical angle after the class. And if you have any doubts, let me know. Text me on WhatsApp. I'll share the solution with you. Note this down. Once you complete it, text me done. I'll stop the class. 1 or 2 numericals and application that we'll do on Tuesday now. Sine IC is equal to 1 by n. See, sine IC is equal to 1 by n from here. Refractive index of this medium is 1 and angle of refraction is 90 degree. So this becomes 1 into sine 90. This is equal to what? Refractive index of this medium multiplied by sine of this. That is n into sine IC. So sine IC from here will be what? 1 by n only. And second query is AB part. AB part also see, wherever is the refractive index, wherever the light ray you are referring to, angle you are taking, take the sine of that and refractive index. Like 1 is the refractive index here, so 1. Angle is sine 70 equal to refractive index of glass n, angle R. So at this interface, I am calculating and I am applying Snell's law. So 1 into sine 70 is equal to n into small r. Now is it clear, or any doubts? If you have, let me know. I'll repeat it once because this is a very important topic. Clear? Okay.
Yes.
Those who have completed till here, you all can leave. Class time
Teacher, can
is.
you scroll up a little bit?
Yes, right. From here.
Yes, teacher. Okay, teacher, you can scroll down.
As soon as you all will be completing it, you all can leave. Your time is already up.
Thank you, teacher.
Thank you, ma'am.